Okay, thank you. So let's push on with the agenda. And our next session, which is Destiny for Weather Extremes and Climate Adaptation. Before we do, however, just a quick word. This beautiful image on the screen behind you has been created by our in-house artist today, Judith, who's standing over there. Right, Judith, do you want to just stand up and give us a wave? If I can just say, this is fantastic. So these are just going to be some very personal, very light touch images of today's proceedings that are going to be captured for posterity. So you'll be able to see these during the breaks and later in the event. But just wanted to let you know that Judith is here. She's not taking any personal pictures or doing caricatures, but this is a lovely addition to the overall knowledge capture for today's event. Okay, so let's crack on. Destiny for Weather Extremes and Climate Adaptation. So this is the first of two sessions where we're going to focus on demonstration and application. And we're going to try and look at the climate and extreme DTs from both a producer and a user perspective. So this means that we're going to dive into some of the details about the latest advances around simulation production, quality assurance, and the evolution of digital twin capabilities. So in parallel, our speakers are going to try to give you some of the storylines, some of the what-if simulations that were referenced earlier in our first block, and really to look at how these simulations can support various aspects of climate preparedness, resilience to climate and extreme events across scales, from local to global, and also to highlight the experience of users of the digital twins and Destination Earth, and how these technologies are creating new opportunities and possibilities for users. So we're going to have narratives. We have 5 eminent guests who are joining us on the stage today to deliver some of their personal and institutional perspectives about how these new technologies and capabilities are supporting their work, giving them fresh inspiration. We will pause halfway through to take 2 or 3 questions from you in the room. And then at that midpoint, we're also going to pop up a QR code for our online audience to submit some questions, which the ECMWF team will diligently filter. And we're going to try and save some room at the end of the session to take 2 or 3 questions from the online audience. Okay, so I hope that's all clear. We're going to try and increase the level of interaction as we move forward. But for now, let's get on with the panel session, and I'm very pleased to introduce our 5 speakers. So, in alphabetical order, Thomas Jung, Professor and Vice Director of the Alfred Wegener Institute for the Helmholtz Center for Polar and Marine Research at the far end. Next to him, we have Marianne Thering, who I think many of you know is the Director General of the Danish Meteorological Institute. Next to Marianne, we have Dirk Lauvert, who's Climate Scientist and Project Manager at VITO here in Belgium. Dirk, welcome. Next to him, Jenny Konkanen, who is the Digital Twins Group Lead at CSC, IT Center for Science in Finland. And last but by no means least, Kun Jan, who is a senior researcher in coastal hydrodynamics and forecasting for Deltares in the Netherlands. Please join me in welcoming them to the stage. So we're going to get things underway with a big picture from Marianne, and in particular how the Weather Extremes DT is really supporting the work of DMI. But Marianne, just give us your big picture overview of how these digital twins are really supporting the ambitions and the mission of DMI.
Yes, thank you very much. Yes, you can hear me. Thank you very much, and thank you for giving me the opportunity to sort of represent the National Met Services in this user meeting, which I'm very fond of being part of. I think indeed it's really motivating when users and of a different nature, we meet each other, and those of us who are responsible also for some of the development, we can listen to each other and understand each other's points of view. I would also like to give you two small fun facts before I start my small presentation. The one is that DMI is responsible for meteorology and climate and ice and water and oceans and whatnot in Denmark, a little kingdom, but it also means Greenland. So to some extent in meteorological terms, we are kind of a superpower. So bear that in mind when you hear what I'm talking about. And the other little fun fact I would like to give you is that we are really, really eager on collaboration, and we are really eager to learn from others, but we also like to contribute to a common development. Am I the one who is managing this? Probably, yes.
Yes.
Whoa. Great. All right. Thank you. Well, as mentioned earlier before in the other panel, climate change and the sort of forecast for Europe means that extreme events will be over us even more than we have seen already today. So what we have been dealing with in the Extremes DT is, of course, to make a simulation framework which allows us to understand what is happening in the world and how will the simulation continue into our regional situation. The global simulations in the digital twins, they are usually given by 4.4 kilometers globally around the world, and we get that from ECMWF, and that's a kind of sort of strong information we get, which we transfer into a regional simulation, which can, as you see, I hope you can follow my explanation on the slide, which will show you a more precise detection of the weather situation which comes to us from the outside world, from the global situation. But what is really interesting for us, of course, is what we see locally, what we see in our cities, what we see in our sectors. That is what we as a National Met Service is really concerned about. And that's why we are more than keen on the regional development. You can see from this presentation and the little film that we get an observation in the first satellite observations. We have a present picture of the operational model, but with the regional extremes, DT, which has a resolution of just 500 meters, we are really getting closer and closer to understand what is exactly taking place in a local area. We have some, at least at DMI, we have some years of experience with very high resolute models, primarily run in Greenland. That was why I mentioned Greenland in the beginning. So we are building on knowledge we have already, and we are really indeed eager to continue this critical information to be given to our users. I would also like to mention that, in fact, running these models the way we do it, in the collaboration we do, means that we collect new data, which is a basis for operating and developing even more AI models and better AI models. So that value chain is really important. In this slide, yes, you can see the way we try and describe and understand value creation from our collaboration with colleagues in the Digital Earth project. Basically, we are focused on safety. We are focused on extreme weather situations. We are focusing also on what was mentioned earlier today, the economic impact possibilities and the green transition. We also focused on science, to improve science and to deliver into science, and planning, the planning possibility the tool of DG has. In general, what we really like to do, and this is what we are working on 24/7 at a National Met Service, that is to enable other authorities, other businesses, everyone who takes decision or choices, to base their choices and decisions on a structured set of tools and data based on science, which gives people the right advice in a difficult situation. And this is exactly what we allow ourselves to understand is the point of the Digital Earth project as such, and the DTs in particular. I would like to now to give you 2 examples on how we more precisely work with how to use the AI models and the DTs. First of all, energy weather. Energy weather concerns the fact that these days, being part of the green transition, which we are, all of us here, I hope, we really have to look at weather, and we really like to look at weather in a different way that we used to do. Not only how to protect ourselves from severe weather situations, but also how to use weather. And in that respect, we really want to know more about resilient energy sources and how our energy markets can rely in an efficient way on wind, sun, and how also to fuel the hydropower plants. Just as one example, solar power, it has now in 25 raised a share of 1/8 of the global consumption, which means that it is something which we have to take into consideration and see how we can help our users in using the best way. I would like to give you an example, and it is in fact from Germany, but it was reported very clearly in a Danish newspaper once, so that's why I would like to give you this one. In June 2019, it's quite some time ago, but still a good example, a large area of thunderstorms passed over northern Germany and in fact Denmark too, and massively reducing the solar power production. Of course, with thunderstorms, not a lot of sun gives you benefit. The weather forecast and impact sector models used at the time by energy traders was rather incorrect or inaccurate, and it led to a massive imbalance of the German energy system of almost 10,000 megawatts. The Destiny Digital Earth Twin system, we have sort of tried to play the situation again. How could this have been grasped by the digital twin? The sub-kilometer resolution means that we have moved from a sort of Minecraft world to something which is far more realistic. It means that the digital twin is able to model the clouds realistically and show that about 18% of the situation would have been modeled much more precise than what we really saw. People have tried to figure out that this event was very costly. The cost of the event is meant to be 58 million euro, and every megawatt we are able to save or find other solutions in the right time is money saved for European citizens. The other example I would like to give you, I hope I have 2 minutes more. Yeah, okay, thank you. It is sort of the very national Met Service classic example. It is an example with a clear connection to the role we have as responsible for warnings for dangerous and extreme weather situations. This example is from September 24. A Danish town, the west coast of Denmark, received approximately 2 months' worth of rainfall under 24 hours, which was a really record-breaking precipitation situation. And there was again a huge cost of 2.7 million euros in the town Esbjerg. Forecast of such an extreme event is challenging for Met offices, not only DMI, but I think all of us. The heavy precipitation on one particular little place, that is really difficult. But Destiny is developing tools which definitely helps us to improve really importantly in this field. Maybe I have, no, I'll go back again. Okay, anyways, we would really like to continue again, in fact, to show this one I just showed you from Esbjerg, is to show the benefit not only for DMI, but for citizens, for the preparedness infrastructure agencies as well, that we are now able to move ourselves from the 9 kilometer example forecast to the much smaller resolution, 4.4 resolution, and then again, now with the extreme DT to talk about a resolution where we use square meters of 500 meters. I think we have to bear in mind being able to connect to this development, which has, to my knowledge, come really, really fast. We have to continue our collaboration, and that's why I would like to mention these 5 takeaways. We are really important being national Met services. We are really important in supporting the green transition. The geopolitical situation of Europe has been mentioned already today. I'm not going to go further into it, but I would like to mention that I think for all governments, energy prices is something which are high on their agenda. So here we have a very interesting field of economy where we can participate and we can deliver results. Open data was discussed in the previous, or mentioned at least in the previous panel. For sure, DMI advocates for open data and open source. That is what we have learned since we, some years ago, opened our data. We have learned that a lot of good things happen when you allow people to do with your data what they like to do. Previously, we were guessing and delivering to people. Now, with another kind of dialogue, I think we are improving much faster. And the last thing I would like to mention as a takeaway from what I have mentioned today is to advance in future this on-demand forecast for the severe weather situations. Being able to do that, it is very, very important that we continue the development you've seen already today, mentioned from others as well, but also that we continue to develop the collaboration between our knowledgeable meteorologists, the agencies whom we are serving, and also in that part learn from each other. Because when you look at the history in Europe, the last few years, we know that it's when the collaboration between knowledgeable people doesn't work perfectly, that's where we lose citizens. So on that note, thank you very much.
Okay, Marianne, thank you very much. So, that's a great way to kick things off, the big picture of institutional value creation with the weather extremes, DT. Now we turn to Jenny from CSC, and tell us a little bit more about how things have been working around the climate DT, and also co-creation of applications and more. But Jenny, please, the floor is yours.
Okay, thank you. So hello everyone, I'm Jenny Kontkanen from CSC, IT Center for Science. And like introduced, I will talk about Destination Earth Climate Adaptation Digital Twin, or Climate DT, like we call it. Okay, I want to start by highlighting that the Climate DT is implemented in a European partnership that is led by us at CSC, but which very importantly includes several organizations across Europe. You can see the organizations there. I don't now go them through, but just wanted to mention this. And of course, we also collaborate closely with ECNWF. So what is Climate DT? We already heard about something earlier today, but briefly put, Climate DT delivers an operational framework to produce actionable climate information by combining kilometer-scale global climate models and impact sector applications. One of the novel capabilities of Climate DT is that it produces multi-decadal global climate projections as well as storyline simulations at enhanced spatial and temporal resolutions. Climate DT also has first ever operational capability for climate projections, and it also has novel capabilities for addressing what-if questions by different users. And importantly, Climate DT in a very novel way integrates climate models and impact sector applications in the same workflow, and this enables this producing of the actionable information. So this last point is illustrated in this schematic. I will go this through step by step. So we have these 3 kilometer scale global climate models. They are called IFS NEMO, IFS FESOM, and ICON. We run them on leading Euro-HPC systems. So far we have focused on using LUMI, located in Finland, and Mare Nostrum 5, that is in Spain. Output of these climate models is standardized so that they follow common format and common data governance, and then this output is delivered to different applications. So this includes applications that perform on the fly, so while the climate models are running, monitoring, evaluation, and bias adjustment. We also have then these impact sector applications, and what they do is they transform this climate data to actionable information that is relevant for different sectors. Then these tailored indicators coming from these impact sector applications, as well as projections and storylines that are produced by these climate models, they are transferred to the data lake and can be accessed from there via Destination Earth platform. Here is an example from one of the applications. Actually, Irina already went this through earlier very nicely, so maybe I will just skip this, but I want to mention that in addition, so we have one application focusing on producing information on wind energy, then we have one providing information on hydrology, one on hydrometeorological extremes, as well as one on wildfires. Then still a few words about climate DT simulations. So like already mentioned, they have enhanced spatial and temporal resolutions. And this is illustrated in this animation where on the left-hand side you can see climate DT simulations. On the right-hand side you can see simulations from other state-of-the-art global climate modeling activity. So in climate DT, our spatial resolution is from 5 to 10 kilometers, while in these current other global climate modeling activities, the resolution is typically 100 kilometers. And in this animation, you can see how big difference there is in the level of detail that we can achieve with the climate DT resolutions. And what this means is that the climate DT can provide global information with local granularity. And here is an example on that linked to extreme rainfall. So you can see there mean of annual maximum precipitations. First, these results are from observations and reanalysis over the Alps. And there you can see some regions with high precipitation values due to the orographic effect caused by the mountains. Then here you can see the same results from CMIC6 global simulations as well as from the CORDEX regional simulations. So as you can see from the CMIC6 results, because of the coarse resolution, we are not able to see these regions that can be observed in the observations and reanalysis, while then in the CORDEX, CORDEX results can capture this pattern of the high precipitation values. Then finally, when we look at the climate DT global simulations from the 3 models that we have, we can see how in these simulations we are able to capture this precipitation pattern over the Alps. And now it's important to highlight that these climate DT simulations are global, so we can get this information at this level of detail globally. Okay, so then finally, I want to still one more time to promote the new simulations as well as user guide that is available via Destination Earth platform. So these new Generation 2 simulations include multi-decadal simulations at 5 kilometer resolution with these 3 coupled climate models, so IFS NEMO, IFS VESOM, and ICON. And these simulations include control simulations, historical simulations, as well as projections until 2050. In addition, there's also storyline simulations at 10 kilometer resolution with IFS VESOM for the weather events observed between 2017 and 2025, and we can soon hear from Thomas more about this storyline approach. And then impact sector information coming from these impact sector applications will also be released soon in the coming months. Thank you.
Jenny, thank you very much. Please invite you to come and sit down. Now, Thomas, just before you step up, I'm just reassuring the panel because the clock's ticking down to 30 seconds. We do have another 45 minutes to go, okay? Not 45 seconds, just to reassure you. We're not going to kick you off the stage. But now let's hear from Thomas and something about the storyline capability. Thomas, give us some of your perspectives on this.
Okay, pleasure. Good afternoon, everyone. It's a special pleasure being here today, this afternoon in Brussels, joining this panel, but in particular also talking about the storylines, the presentations which should be coming up any second by now. And I should be saying that this is a topic, for those who know me, that is very close to my heart. And it's about replaying extreme events. We have heard this a couple of times today under different, climate conditions. And this is really something that is helpful in sort of making tangible what climate change actually means for certain events and hence supporting us when it comes to climate adaptation. They're sometimes called storylines, sometimes counterfactuals, but they are pretty much all the same. So what's the motivation for this? It is about extreme events. We are experiencing plenty of those recently. And I would like today to touch on two. I mean, obviously, these record-breaking temperatures that we recently experienced in France is a prime example for that. I will be touching on that. Another are the floods. We had a few actually flooding events in autumn 2024, and I will be touching on the ones that hit the Alps and eastern parts of Europe as well. But whatever kind of extreme event we are experiencing, there are always two questions emerging. And the first one is an attribution question, sort of how much of that is climate change? And then the second one is probably a projection question, sort of how much would this change further if we were to approach, I don't know, a 2, 3, or 4 degree warmer world? And there are different ways of addressing these type of questions, probabilistic ones, but there are also these sort of very intuitive storyline techniques that I would like to introduce. Now, this is about how it works, about replaying certain weather or environmental events. We're actually not just using atmospheric models, but coupled models. So it's about coupled environmental extremes that we can replay for different climates. And we can do this for present-day conditions, so taking a coupled model and sort of running it by sort of nudging and prescribing the evolution of the upper tropospheric wind, the jet stream. Do this in present-day conditions, do this for pre-industrial conditions in the future, and then you have those replays ready for analysis. So the same event replayed in different climate. And it works, as we will see on the next slide, actually quite beautifully. So spectral nudging keeps the observed weather pattern or system in place. Then, this is combined with a kilometer scale twin, that allows us to give local granularity everywhere on this planet. And then, we do have these stories. Now, does it work? For it to work, we have to demonstrate that it can actually replay our previous weather. And these are time series, I think, that are making the point. What you're seeing is two curves. The black curve is 2-meter temperature for Brussels since the 1st of January 2026. Sort of temperature slowly going up, and they're up and downs. The second curve, that's very similar, is the replay from the digital twin, okay? And you clearly see that it's nicely following the up and down, sort of the weather systems coming and going. Now you may say, but they are not perfect in perfect agreement. But that's a feature, that's a must, because we only prescribe the large-scale circulation. The thermodynamics of the model and mesoscale processes, they are left free, okay? And that's needed for the system actually to respond to climate change. So these departures for the present day are critical, a critical feature to make that possible. Climate change, I think it's also very telling beyond extremes. Now, what is climate change doing? These are the time series, and you see that climate change at almost constant, but sometimes there are variations, increment to temperatures, right? I mean, again, the black curve is what was observed. The blue curve is replaying the last few months under present-day climate conditions. And what you see is these curves never overlap, right? They're always apart from each other. So every single day, there is an increment that we can quantify with this kind of technology. And if you look into the future, this sort of departure becomes even larger. Sometimes you hear people saying climate change is not impacting weather. Well, 2-meter temperature is probably one of the foremost weather parameters in the world, and clearly we see it does. What people mean is we can't really say much in terms of weather systems, right? Sort of, that's a different story. But the weather associated with the system that once it has developed, we can really determine the impact of climate change on that. Now let's have a look at these two examples just to get a bit of a feeling for this. This is Storm Boris. I'm quickly replaying this here. You see it in different worlds. It's a nice animation, nice visual, but you can also be, quantitative, and you see sort of the accumulations for the different worlds on the right-hand side, 2 degree warmer, on the left-hand side, pre-industrial, ramping up, and then you can quantify that to the region, and you see something like, a 24% increase in 2 degree compared to present day. That's for an area. If you go into certain levels, valleys of the Alps or something, these departures may be different. Very briefly, when you see these kind of events, you may be tempted to believe that, every extreme precipitation event is increased by something like 7% per 1 degree global warming. But that's not true. These extreme events that was, sort of precipitation event that was mentioned earlier this morning in July 2019 that had Belgium and Germany didn't show any changes in these kind of simulations. And there was a flood in Texas in the US last year where we see that in the warmer world, convection and precipitation actually dies down. It depends on the event, it depends on the region, and if you want to adapt and want to have the best possible knowledge, you better take this into account. And I guess the storylines are one way to quantify that for different events and different regions in the world. Let me sort of finish with looking at the European heat wave. The numbers are quite small, but what you are seeing is that this 2 degree warming, the event without global warming was extreme. That's probably not a surprise with this heat dome developing, but from the simulation, it looks like the event in the 2 degree warmer world would be 2.5 degree warmer than it was. Now, this may not sound a lot, and we know probably bigger numbers from heat waves in summer, but this was an early summer, spring heat wave, probably where we still had a lot of moisture in the ground, and this moisture can evaporate and cool. So as we go into the summer, these increments become larger as basically the air conditioning of our system is shutting off. Okay. This is now here then the last slide, very briefly. So I think storylines do not replace something that's there. I think they add to our toolkit that we need in order to take informed decisions. They are complementary. I think they are tangible. They provide local information, and we are working on making them available in near real time. And that's something we should be rolling out later this year. Thank you very much.
Okay, Thomas, thank you very much. So we're going to take a few minutes to give you the chance to raise any comments, ask any questions that you may have. If they are broad enough to also allow Dirk and Koen to jump in, even though they haven't made the short user case presentation yet, all the better. But let's just see. Anybody who would like to ask a question or make a comment, please feel free to raise your hands. And we have a couple of team members ready to circulate with microphones. If not, we can keep going. Oh, we have one. Congratulations. You win first prize, big gold star. And if you could just introduce yourself.
So, hello, my name is Bente Liljaby, come from Norway, and I'm a partner in the Clerio, which is worked with ECMWF. My question is, when you see all these models and you see the twin, how do you see the effect of not getting the local data from around the world? I mean, we have Europe, so we have a certain chance to get the data from Europe, but how about for the models? Does the other, for instance, the Global South, which is lacking information and data, how does that influence the accuracy of the twin? Thank you.
Okay, excellent question. Thank you. I wonder if, is there a second one that we can take now? Yep, there's a hand towards the back. And was there a third one? Yep. So over on the right, in the middle, on my side, when we've had the second question. So gentlemen, if you'd just like to introduce yourself.
Yes, I'm Miguel Cordova from Ocean Winds, wind developer, offshore wind developer. I'm very keen about the storylines because I have just like a very root question. How many times do you guys go backwards to initiate the simulation? Because it could happen that if you run the simulation, the atmosphere may just decide that it wants another thing, and you may have another scenario. So perhaps the heat wave will not occur, or perhaps the precipitation will go, rather than Vienna, to go Ljubljana.
Okay, I just asked, did you understand the question? Because it's... Yeah, so
what?
Maybe if you could just maybe move the microphone away a little bit and just
okay,
repeat
sorry.
it simply.
Is getting better?
We can hear you, but because of the sound system, it's very loud for us, so it's not very clear.
Okay, I will try again. Perhaps I will speak slowly. The question is like, how many time steps do you go back to initiate the storyline?
So how far do you go back to initiate the storyline?
Because I believe that perhaps if you go backwards, go to the past too much, the scenario may change and you won't have the same event happening.
Okay, thank you very much for that question. Now we had one more, I think, over here in the middle. Same routine, just introduce yourself and off you go.
Hello, my name is Genevieve Walker, and I'm with the Global Climate Resilience Intelligence Network. So my question is how you are considering Earth's effective warming, post-aerosol masking, Earth's energy imbalance, and tipping point risk once we surpass 2 degrees and 3 degrees Celsius. So how is that incorporated into each of your different models?
Okay, so if we go beyond the plus 2 degrees tipping point, how does that affect the design of the models? Yep? Is that correct? Okay, so let's start with the global data. Marianne, I'm going to give you the global data one. Thomas, you get the storylines. And then for Dirk, Jenny, and Kun, if you want to jump in on any of those, and also the 2 degree tipping point, very happy for you to do so. Marianne, would you like to start with the question about the... Okay, Thomas goes first then.
Okay, so yeah, I mean, I think the first one was on the data, right? I mean, we need data, I guess, to validate our models. That's absolutely critical, right? And improve our models. I mean, validation is one, and improvement is another one. And I mean, at the moment, it's a very pragmatic approach, right? We are taking what's there, and hence we depend on availability of data globally. I mean, and what's going on currently geopolitically, and the systems being taken out of the deep ocean and stuff. I think it's a serious setback. It doesn't just impact us in the development of our systems, but I think that's serious concern. Global South, of course, this is another dimension. I mean, the kind of data that we are producing, the quality is quite high, and I think it would also be very nice that people in the Global South would have access to those data. On the storyline ones, I mean, I think I still quite get it. I mean, it's challenging up here to understand the questions, but it was about initialization of storylines. Perhaps just let me say a couple of words how this is done. I mean, basically the starting point, I mean, since we're doing coupled storylines, are sort of long simulations, classical multi-decadal climate simulations, historical and projections that are used as initial conditions. So once they enter present-day climate, we take a snapshot and then initialize those runs, and then we do the same in the future and in the past, and then we don't just run one experiment, but we run 5 ensemble members. And in principle, given enough computational resources, we could ramp up the ensemble size as well. But that's in principle how it's being done, and from the diagnostics and the analysis, I mean, that looks very convincing in terms of replaying, the weather. That's, I guess, as much as I would say on initialization of the storylines.
Okay, and I think the other part of the question was how far back do you go? How many timescales do you go back to start the storyline? I
mean, these storylines, in principle, we run them in time slices, right? I mean, the time slice we are running is always, the weather from 2017 basically to today. And then what is it? I mean, it's a 9-year, 10-year period or something like that. And this 9-10-year period, we run under present-day conditions, 5-member ensemble. We run it in the past, and then we run it in different futures, 2, say, 3-degree warmer worlds. So it's always time slices of something like 9 to 10 years we are running.
Okay, super. Now, the third question, tipping points. Global temperature increases 2 degrees. How does that influence the design and the functioning of the models? Would anybody like to offer any thoughts on that, or insights, if you have them? Thomas again?
Okay. Yeah. Just very briefly on tipping points, perhaps 2 aspects on tipping points. I think sort of, are our systems tipping point aware? I don't think they are at this stage. I mean, neither are, CMIP 6 models, and probably not most of the CMIP 7 models. I mean, certain important processes are missing in our models, like ice sheets, for example. In principle, we have the AMOC, the Atlantic Meridional Overturning Circulation, and that's in principle a tipping element that, is potentially there in our models. But we are clearly lacking some, like permafrost, like the ice sheets. But in principle, in a later phase, that's something that could be added. A second element to this, what we can do though is, we can replay and use the storyline actually approach to see what a tipping element, if it would happen, what it would mean to us. Because we could also ask, how would this extreme event or the weather today look like if the AMOC would have collapsed? And we've done actually with lower resolution model experiments doing that. So this what if capabilities, it's not constrained just to climate change, but we can also use it to see what if a tipping point would have passed, how would this affect weather, on this day, extreme events and so forth. Nothing is stopping us, and I think that's a very interesting direction to go.
Fantastic. Thank you very much, Thomas. Now, if the panel have other comments, I suggest we park them for now, because Kun and Dirk have been sitting here very patiently. So we're going to shift on to a couple of short sort of user perspective presentations. Kun from Deltaris first around extreme precipitation management, and then Dirk from Vito around urban heat mapping. But Kun, share us your experiences from a user perspective.
Thank you, Simon. So I'm going to give a sort of journey to walk through how we get here in terms of flooding. Flooding is one of the important, I would say, impact sectors for application of extreme DT data, including extreme DT and climate DT. So to do that, you need a few building blocks. So I think Deltaris is lucky enough to participate that from the beginning. I'm going to describe how do we address the compound flooding, both in terms of extreme event forecasting, but also climate adaptation, also from decadal, multi-decadal simulations to so-called storyline simulations. Now compound flooding is becoming, basically visible everywhere, right? You say the phenomena is there. You have the threats from the coastal areas, but also from the inland snow melting, but also extreme precipitation in a river, and then those both would meet somewhere in the urban deltas that exhibited the flood impact, especially on the sea level rise and climate change, right? So you do need a tool or a framework to simulate this type of impact. So for that, we come up with something with compound flood workflow. Basically consists of several models, numerical models, try to address each flood driver separately and try to combine them, assuming full independence, combine them, and then see how the flood evolves. So and this is the first steps to test the workflow, and with extreme DT data. We do see high-resolution extreme DT data provide advantages, for example, in extreme precipitation, as you can see on the right, top right-hand side. But there was a lot of nuance to that. Does not necessarily mean your catchment modeling, hydrological model simulation will immediately increase the output. So there's the same for the flood inundation simulations. But then say, because extreme DT or climate DT provide a global system, so we can sort of take advantage and make so-called global to local flood services. In this time, we focus on flood forecasting pilot services. We use the same workflow, but zoom in to local areas, in this case, Philippines. We team up with Red Cross 510 in the Netherlands to look at impact-based forecasting and early warning, providing messages in case of cyclone strike and also the flood impact. So in this case, we can easily make use of extreme DT operational data to build such a service to improve the early warning and preparedness. That's one of the also a pilot service, if you like, applications. And then, of course, climate change is important, and how can we make use of so-called climate storylines and try to understand the current climate versus, for example, 1950 pre-industrial situation, that how, in this example, the same tropical cyclone Idai in Mozambique will impact, with its flood risk impact in the pre-industrial era versus now. We can see, thanks to actually the climate DT scenarios simulations, we do see an increase of the precipitation and wind for the current climate. And then we can actually assess its impact. This is actually done in a Compass European project. And then if we have those simulations, we can understand how flood adaptation strategies works, right? There was a lot of what-if questions you could answer, both from the phenomenal point of view, but also from adaptation strategy point of view, where we can build a seawall or improve my drainage system. How would that strategy will react to the future climate scenarios? In combination with storyline simulations with a platform called Flood Adapt that users can come together and discuss various strategies and then change the strategies and see the reaction of the flood risk, and then try to come up with cost-benefit analysis and how to react to, how to design the best strategies forward. Building based on all these components, we have the modeling of the flood risks, we have the adaptation, we have capabilities of integrating everything together. We could also looking at a large scale, for example, pan-European climate risk assessment for flooding. And there we could combine one of the data sets from eXchange from the destination Earth, also from C3S, and then leverage based on this framework and try to understand the flood risk indicated for the whole Europe. And then we can also zoom into local areas by using those type of storyline simulations to really dive into details on how each sort of infrastructure level, how the flood risk will look like. Last but not the least, we're also working on AI. So instead of a sort of traditional AI, traditional physically based model, you can replace that with perhaps faster ML emulators, and also you can build agents based on large language model, try to sort of help the non-technical users to interpret and interact with such a complex model change. So this is something we're also building within Destination Earth, especially on the hydrological modeling and water quality towards water resilience. That's my short summary about the entire flood-related.
Good, thank you very much. It's a great example, and we love the pan-European application potential. I think it's fascinating. You'll be around for the next day and a half, right? People want to learn more. So now, last but by no means least, Dirk.
Okay, thank you. All right, good afternoon, everyone. I'll be short, I promise. I'm Dirk Lauwert from VITO, the Belgian Research Institute, and we've been developing over the past years a urban heat service in the framework of Destination Earth, together with Tecnalia, a research institute from Spain. Yes, so we focus on urban heat stress because, as you know, cities are on the front line of climate change. Heat waves are increasing, and the impact of heat stress is certainly felt very hard in cities because of the urban heat island effect, so the fact that air temperatures during the evening and the night are higher in the city center compared to the rural countrysides. And this has a strong impact on human health, on the health of people living in cities. And we focus on downscaling global climate results to the very, very local scale, to the street level scale, because this is the scale at which local policymakers and action planners can do something. They can implement some measures on a very local scale. And for these type of things, they want to have quantified information, they want to be well informed about the things they do. The global climate models, even if they have a very high resolution, they're not able to answer these detailed questions that these people have. I want to emphasize here that we are developing our service together with the cities, not only from a researcher point of view, but really try to listen to the stakeholders and the urban planners, what they really need. In our project, there are 4 city networks involved, and we are developing the service for 8 pilot cities, with which we all have meetings and try to see what they really need from us for their work. So what are we doing? We are downscaling, like I said, the global climate information from the climate digital twins with a physics-based urban climate model that we developed in VITO in-house, which is able to downscale heat-related variables to 100-meter resolution. So quite a high resolution already, but we go even a step further, and we also take into account radiation, shading from buildings, from trees, because this is very, very important for human thermal comfort. And in this way, we can go to 1-meter resolution heat stress maps for these cities. There's a small example in the movie there. It's for the city center of Lisbon. And then you see for a typical hot summer day, how heat stress is evolving for a typical part of the city. You have a park on the top left corner of the image, so you see it's always a bit cooler there. But you also see, when you see the temperatures rising over the day, that the areas that have tree and building shade are much cooler than the areas that don't have this. And of course, we do this type of simulations not only for past events, we only look at the future. We run some adaptation scenarios for these cities so that they can take well-informed decisions on where to take measures regarding heat stress. What is the added value of Destination Earth for our work? So there are a couple of things. Of course, the very high resolution climate digital twins, they provide better estimates of land-sea interactions, mountain effects, local circulations, which makes also our projections better and more correct for these locations. We can access the data through the data lake with APIs. It's very efficient, it's very automatic, so that's very nice. We are trying to onboard our service in the service platform, which also gives us added functionalities and of course a very big user community that can make use of our services. And last but not least, I think there is a big potential in the Destination Earth and Climate TT for having more global or European-wide policy adaptation scenarios that can be run with the models. Because, I mean, these cities can take local measures, that's also what we calculate, but the impact is there's there, but it's not very big. This is an example for the city of Milan, where we calculated or estimated the number of heat-related mortality based on detailed temperature data combined with detailed population data. And you can see, due to climate change, if nothing changes in the city and people do the same things as they did before, then the mortality will increase quite a lot by 2045, according to SSP 3.7. We can implement, or cities can implement things like green roofs, they can plant some trees, they can do some soil unsealing, and these type of measures will have an impact, and there is a noticeable effect on the mortality, but it's not enough. I mean, we're not getting there. We also have to look at local health action plans, looking at the buildings, what we have to change indoors, how we have to protect people. But also on a more global scale, I think, at the local scale, the cities can do something, but maybe at the European scale or even globally, we can do more to prevent this type of climate scenario, to try to lower the absolute rise in temperatures at a more global scale. And this is also something that climate digital twins can provide more information on, I think. And finally, I would like to, of course, acknowledge all the people that are contributing to this work. And if you want to know more, you can visit our demo stand in the next room. And happy to talk to you or to discuss all the things we do. Thanks.
Thank you very much, Dirk. I think you missed the memo. There's no QR code on it. There's no QR code on it. I think you missed the memo. That's for next time. Okay, so we have about 15 minutes left, and we did promise that we would try to take a couple of questions from the online audience. So I'm just having a quick look to the back of the room to the colleagues from ECMWF. Is it possible for us to get one or two of the questions posted on the screen in front, and then we'll see what our panel makes of those. And then I have one closing question for all of you about uptake, selling the message, communicating the value of these applications. But let's see if we can get the questions on the screen. They are on the big screen behind us. So I tell you what, you sit there, I'll stand, and then I'll read the first one to you. Okay, so first question. How does the Extreme DT activation work? Is it a national authority or authorized user to activate it? Or is it something automatic based on some variable anomaly? So I think, Marianne, that's probably going to land with you. Question 2, is there a way to measure the, we can see it on the screen now, to measure the uncertainty associated with the storyline simulations? Is a single model sufficient despite the impressive high resolution? And the third one, without my glasses, impressive advances in the climate weather simulations, including improved granularity. What are you learning from non-expert users, e.g. policymakers? How can they keep up with simulations and Destiny services so they can use information to support decision-making? What's needed in 6 months' time? So maybe Marianne would give you the first one. And then I think, Thomas, you're probably going to come back to the storylines, but I'm also keen to hear about your thoughts on this third question, including Jenny, about the non-expert user experiences. But Marianne, why don't you kick us off with the Extreme DT question?
Thank you very much. It seems to work this very good. I really think the question is most relevant, because what it holds a complex answer, because it holds an answer, or it covers also an answer which has to do with the whole organizational change we have to make in a national Met Service to make sure that we, in fact and in practice, do have benefits from what we are inventing in the floor of the scientists, the digital twins. What we imagine is that the sort of parallel development between what takes place in the world of the scientists and the meteorologists or the forecasters is that the forecasters will ask for the DT to be put on, sort of thing. I mean, we know quite a lot about weather in general, so we will know that something is going on. And because it's very costly to run these models, we will not be able to run the model all the time, and it won't make sense. But we will train the meteorologists and the forecasters to ask for the digital twins. That is what we have done in Green, and in case of Green, and I told you in my intervention about that we have a little practice and little practical knowledge from having high-resolution models in particular areas of Greenland where there are very heavy winds or storms. But we don't run that very high-resolution model all the time. The meteorologists, they ask us to put it on. So I think it has to be a very close collaboration between the weather room and the scientists, and to some extent our data scientists as well, to make sure that we can run the whole sort of value chain when needed. And it comes with a lot of training, and it comes with a lot of common understanding between all these different people. And it's not going to be so easy. And the other thing is, we will also, sorry, I would like to give you a short answer, but this is complicated. We also have to train our users. For instance, the preparedness people, the police, everyone should understand what is taking place. We are advising people when heavy weather situations occur, and we will do that in future, but with a new element. And we have tried that, that's another story, but we have tried that in one case already. So you have to make users, the real users, the customers, to make them believe that this new product is really worth believing in. And that doesn't come all by itself. So there's a lot of organizational development within the success of Destination Earth.
Okay, thank you very much, Marianne. I guess actually, Jenny, maybe I should ask you, does the same situation apply for the climate DT in terms of activation, or is that not something that you're working on directly?
Does this work?
It should be on.
Okay. Does it work? Yeah. Okay, it works. Yeah, actually in climate DT the situation is a bit different because we don't kind of activate it. We run the long simulations for the future kind of continuously as part of the operational cycle. So it's in that sense a bit different situation. Yeah.
Okay, very good. Consider me enlightened. Thomas, let's hear from you on the storyline question, the uncertainty and the single model despite high resolution.
Yeah, okay. Is there a way to measure the uncertainty associated with the storyline simulations? The short answer is yes, we do have a 5-member ensemble, right? I do appreciate, though, that we need to learn a little bit what that means. It's not directly comparable to classical ensembles we are used to in climate research. So I think there's a bit of a learning curve there. The second question is a single model sufficient despite the impressive high resolution? I think it's a very good starting point, but probably I couldn't say it's sufficient. I mean, it would be nice. It would be, let's put it, it's a very good starting point. It would be nice to to have, you know, one or two models just to see whether there's sort of fundamentally a different answer with that. Having said that, I think it's fair to realize and sort of point out that there are similar type of systems available as well, as the so-called pseudo-global warming systems that are run with different models. And in principle, we could sort of compare the fundamental mechanisms that potentially give rise to changes in the warming world. So we have a poor man's multi-model ensemble, I would argue.
Okay, fantastic. Now, dear Kun, Jenny, on this third question in particular, but if you have any further thoughts on the first two, please feel free to chip in. But let's come to the users if possible.
Maybe just to add a little bit to Thomas about the uncertainty associated with the storyline simulation. What we see, for example, in the tropical cyclone EDI simulation is that, I don't remember exactly, but 4 out of 5 ensemble members of the precipitation in the current climate is higher consistently than the pre-industrial one. So that means, I mean, if you show me one single realization with very high resolution, but my question is, what would be the uncertainty? How reliable I think your simulation is? But if most of the realizations are consistently higher, that means it includes some sort of uncertainty. So this gives more confidence actually to our impact modelers to understand the whole credibility of the storyline simulation. So that's a little feedback I would like to give. On the third question about how non-expert users could keep up with the development Destination Earth, I think there are like 2 ways. One is Destination Earth provided a lot of demonstrators and pilot services, and those are, interpreted results based on the raw data of destinations are translated into impact sectors with meaningful indicators or operational data sets. In that way, I think it's sort of indirect way to keep up with not only the increasing resolution of the data set, but also what happens in the development of the impact set, advanced flood modeling, for example, workflows, etc. Maybe, just to add, maybe AI or large language model could help to close that gap, that non-expert could just interact with the natural language and try to pose their questions and get meaningful information back. Of course, there is uncertainty there. We should be using with a great caution, but that's, I think, one of the areas could worth look into.
Of high potential. Great. Thank you, Kun. Dirk, you'd like to go next?
Yeah, maybe I can add something on this third question. That I think for non-expert users, even for more expert users, this is a very technical story. So it's very difficult to keep up with everything. I think like you mentioned, it takes a lot of communication, lots of training to get people to believe in these results, to actually use them. I think for now, what I see from the service platform, and there's a lot of very technical things there. Maybe some more examples of co-developed services could help there. I think good examples. A lot of cities, they learn, or other policymakers, they learn from others. They look at what others are doing. So if there are a lot of good, useful examples on there, I'm quite sure that the uptake will increase quite a lot. Yeah.
Okay, yes, you can briefly, and then I have the final question for the panel. We have just over 5 minutes left, but please go ahead, Jenny.
Yes, still. Also related to the third question about these non-expert users. So I would want to hear, kind of repeat what Irina was saying earlier, that also these kind of data brokers like Met Services can be really in a key role here, because they understand the users, they understand their needs and what kind of information they can take up. So just wanted to kind of repeat that.
Very good, thank you. Okay, so 5 minutes left, 1 minute each, final question. We've heard a lot earlier about the importance of user uptake, the importance of clear communications and selling the value proposition of Destiny and its capabilities. So for each of you, what do you think are the most powerful messages to sell the capabilities of Destination Earth, the value of Destination Earth, to key stakeholders, whether they're in policy or whether they're more in the world of practice, climate preparedness, and emergency response? Kun, would you like to go first?
Key messages. I think, this is really from weather and climate data into meaningful or smart decisions, right? So, let's say the Destination Earth community is building the underlying infrastructure and data set, whereas the, say, impact sector practitioners try to build demonstrators, pilot services to bridge the data into
let's say, the real decisions. So I think this is something that we should look forward in phase 3 in the future, to build more meaningful demonstrators and services, to improve the resolution of the data set, explore more, and that's my.
Okay, very good. Jenny, over to you.
So my thoughts are very well aligned with that, because I would also say that in Destination Earth the key is that we don't only produce data, but we produce this actionable information and especially actionable information at these very at the scales where different communities, cities or regions experience the effects of climate change. Then I think the other important point is that in Destination Earth we have capabilities also for tailoring this information to address some specific, for example, policy relevant questions, and that way support, for example, adaptation planning.
Okay, super. Thank you. Dirk, you next.
Okay, yeah. To me, I think the big value lies in what has been developed now. These storylines, these what-if scenarios, I think they provide a lot of added value, and they can really increase the uptake of the results of Destination Earth. Yeah.
Okay, super. Marianne, you get the penultimate word.
Thank you. 3 words. First of all of us dealing with these fantastic developments, we have to showcase well what have we done or what are we able to do, and we should do it together to make very clear pictures to citizens and to politicians. Secondly, we should continue to collaborate. We really have to stand shoulder with shoulder, because this is very complex and it's difficult, and it needs a lot of competences and collaboration. So that was the second word. And the third one is that we have to keep the ambitions high on the agenda, not only our own agenda, but also the agenda of the politicians, because this is a costly development. So if we want that to happen, we have to be able to explain our needs rather clearly if we should be successful.
Very good. Thank you, Marianne. Okay. Thomas, final word.
Yeah, thank you very much. I mean, I think it's it's great to see how far we have come in the last 2 years, and this has been mentioned several times. I think we have developed a very nice software infrastructure, right? That's what it is. And I think using it now and producing data, I think this will be absolutely critical to the success. And I think if we do that and further develop our infrastructure, I think we will be in the position, more or less for the first time, to test choices really before trying them or doing them and implementing them in real life. So I think that's very, very rewarding and a great opportunity.
Excellent. Thank you very much, and also for the concise responses, because we started 5 minutes late, we're finishing 4 minutes late, which means we've saved a little bit of time. Congratulations to you all. Please join me, first of all, in thanking Kun, Jenny, Dirk, Marianne, and Thomas for all of their contributions to this session. Thank you also to our audience online for their questions. We very much appreciate that. It's time for us to take a coffee break now. We're going to try and get